Okay, welcome everybody to the Rocky Mountain Mathematics Physics Seminar. And our speaker today is Professor Andrew Hamilton from the CU Boulder, the Astrophysics Department, and he will speak about Clifford 11.1 string theory.
Thank you very much, Marcus, for the invite, and I apologize for doing this, wedging myself in at the end of the semester when there shouldn't have been any room, but thanks for allowing me to do this. Anyway, I am a big fan of string theory. I think it is the most promising theory of quantum gravity. Really, I do think that. But it's quite clear that string theory has gone, it's been spinning its wheels now for at least a decade, possibly 2 decades. The biggest problem is that we were told that string theory requires supersymmetry, and I'm going to push back on that today. I'm going to ask that no, it does not require supersymmetry. And if it requires supersymmetry, then it was expected that there would be seen evidence for supersymmetry, superpartners, at the Large Hadron Collider, not far above the weak scale, because if it were any higher, it would bring the mass of the Higgs boson up to some higher energy than is seen, which is 125 GeV. So I'm going to start out by reviewing the arguments against old-fashioned bosonic string theory with any supersymmetry at all. You can find these arguments in any of the textbooks, but I'll take it from Polchinski. There's 2 principal arguments. Firstly, there's a statement that only supersymmetric strings admit fermions. And secondly, that the ground state of bosonic string theory is tachyonic, which means it has a negative mass squared potential, and that means it's unstable, and it cannot describe the vacuum that we see today, which is evidently stable. I've already mentioned this, I should also mention that supersymmetry was essential to the first and second superstring revolutions, and so has become part of the canon. And again, I'm going to push back on that idea. So let's examine this idea that only supersymmetric string theories admit fermions. We had a paper. I keep having my papers rejected because they push against the standard conventional wisdom. But what I say is mathematically correct, so I will stand by it. The 2 referees both agreed that bosonic string theory does not admit fermions, and therefore my theory, whatever it might have been, is incorrect. However, I went back and I looked at the textbooks and I looked at the literature very closely to just, why do you insist that supersymmetry is necessary for fermions? And the answer is that if you insist that strings are fermions, then yes, you have to have supersymmetry. Supersymmetry is a symmetry of the kind that we do not see in physics. The symmetries that we see are those of the standard model, U1 cross SU2 cross SU3. Those are all bosonic symmetries. And there's gravity, which has got its own set of symmetries and is based on a spin-2 particle, which is also bosonic. So if you look carefully, what you find, it says, for example, in Becker, and Schwarz, which is...
There are only bosonic, there is no 26 dimensions or something?
We're going to get to 26 dimensions. With supersymmetry, there's 10 dimensions. Without supersymmetry, there has to be 26 dimensions. But first, I have to push back on supersymmetry, because that's where the string theorists are. And if you don't push over that barrier, nothing's ever going to happen. Okay. What did it say? The spectrum of both open and closed strings does not contain fermions. That's in Becker, and Schwarz, which is the 3rd of the canonical textbooks, being Green, Schwarz, and Witten, Polchinski, and the latest one, Becker, and Schwarz. They say the spectrum does not contain fermions, and that is correct. If you make fermions into strings, then you must have supersymmetry. But the original place where string theory began was at the late 1960s, early 1970s, as a theory of the strong force, in which the strong force, the mesons, pions in particular, were envisaged as being strings connecting quark, antiquark pairs. And in that theory, the fermions were not strings, rather they were the endpoints of strings. And this is in Green, Schwarz, and Witten, the first of the canonical sets of textbooks. There is a red quark and a blue antiquark connected by a string. and they talk about an open string with a quark at one end and an anti-quark at the other, and they put them in quotes here. And there's a footnote. By quarks and anti-quarks, we only mean labels representing certain quantum numbers. To attach mass or spin at the ends of open strings would ruin the analysis described in the previous chapters. Now, that's a bit of a vague statement. What analysis? You referred to a whole bunch of previous chapters. Well, if you look closely, what those previous chapters were about was taking strings and quantizing them and finding a spectrum of bosonic excitations on those things, and finding if you want to have fermionic excitations as well, then you have to have supersymmetry, which means there is, for each fermion, there's a partner, a bosonic partner, and vice versa. You can see that they're kind of bothered by this statement. They put it in quotes. Here's this theory which has these things at the endpoints, but I can't believe that it can be the case. As a practical matter, this well describes the strong force as well as the other forces that we see of nature, the other standard model forces. That is to say, a red blue bar, spin one, glue one, is in fact algebraically, mathematically, an outer product or a tensor product of a red quark and a B antiquark. And I'm told by my Cambridge friends who I visited last year that quark is the correct pronunciation. Well, part of the issue is that the endpoints of strings remained a mystery until 1995, when Joe Polchinski finally published his idea of D-branes, which are defined to be surfaces upon which the ends of strings can terminate. So this is a massless gauge boson. The eigenstates of strings have various states. There's a first excited state which produces massive massless gauge bosons, and then there's first, second, and evenly spaced Kaluza-Klein ladder of states going up to very high energies. And the physical eigenstates are transverse. That is to say, they wiggle up and down, and the wiggling of the endpoints is not something that's physical, just like the transverse nature of the gauge bosons, like photons, that we see in nature. Now, if fermions are at the ends of strings, they occupy a D-brane along the end of those strings, and the oscillations of the D-brane are orthogonal to the oscillations of the gauge boson. Here's the D-brane oscillating in its transverse dimensions, and notice it leaves the gauge boson unexcited. And likewise, the gauge boson leaves the fermion unexcited. So the Green, Schwarz, and Witten puzzle that you can't have physical quarks at the ends of strings is just a plain misconception. 1995, the discovery of D-branes was 10 years, more or less, after they wrote their textbook. So when they may be forgiven for doing that. But it should have been the case that in 1995, that whole idea of is open string theory okay, it should have been revived. And it was to some extent, but not very much. I'm just adding here, you can add interactions by putting in a two-dimensional Dirac action or one-dimensional Dirac action along the endpoints of the string, but I'm not going to go through that piece of mathematics. So let me go on. So the first statement that bosonic string theory does not admit fermions is wrong. It doesn't admit fermions as excitations of a string. It admits fermions as endpoints on D-branes. So the second objection, the second standard objection, is that the open string bosonic theory, its ground state is unstable. It's tachyonic, which means it has a negative mass potential. Now, you should understand that the tachyon is not nothing. It is the state of zero excitation of the string. There it is. Nothing's happening. The D-brane is not excited, and the string is not excited. And it is the zeroth level of that Kaluza-Klein ladder of levels. The massless things are at the first excited level, and below that is the ground state, and that ground state has negative mass, which is problematic because it makes it unstable. Now, those properties, okay, I should also mention, of course, it has, unlike a gauge boson, which carries charge, The tachyon carries 0 charge, it's got no excitations, and it carries no spin, so it's a scalar. So in these properties, it resembles exactly the properties of the Higgs boson, which are familiar in the standard model of physics. That is to say, the Higgs boson is itself a multiplet of the symmetry which it breaks. For example, the electroweak Higgs boson is a multiplet of the electroweak symmetry. The U1 cross SU2 symmetry is a 4-component thing. And when it breaks, 4 of those components disappear and become eaten as masses of the Z and the W bosons, and one boson remains behind, the one that gains an expectation value and produces the 125 GeV boson that we see today. In its ground state, where the Higgs field vanishes, it sits at the top of this potential, this Mexican hat potential, which has a quadratic negative mass term, and then a quartic term which stabilizes that potential, and it gets to be more important at larger scales. So that state is tachyonically unstable, and in practice it slides down and goes down to its minimum right there. We call this state where phi equals 0 the false vacuum, and the one at finite expectation value as the true vacuum. Now, this is a very obvious idea, that the tachyon should be the Higgs field, a very obvious idea, and indeed that was pursued. However, there was a stumbling block, which is that what does the potential of the tachyon look like? Because it's string theory and the scattering amplitudes were quite well understood, this was something that was quite feasible. And remember, Joe Polchinski came up with D-branes in 1995. So the idea of looking at open strings instead of the supersymmetric string, the open bosonic string theory, was revived in 1995. And in 1998, Kosteleski and Samuel did the first tree-level 4-point calculation, which was going to be the first contribution to the quartic coefficient of the tachyon potential. And unfortunately, they found, instead of a stabilizing potential, a positive phi to the 4th potential, they found a negative one, which meant the tachyon was even more unstable than you thought of before. And that seemed to be confirmed by a number of other calculations, which made additional assumptions to ease the calculation, supersymmetry, and they also came up with the same conclusion. However, yes?
Tachyon doesn't mean that there is something faster than the speed of light.
Sorry?
Is there something that faster than the speed of light?
No. Yes, thank you for that question. Tachyon is faster than the speed of light in the sense that if you have a wave equation with a negative mass squared term in it, that would correspond to waves moving faster than the speed of light. All it means here is just a kind of a jargon term. All it means is that the potential has a negative mass, whereas if you had a positive mass thing, it would look like it was a quadratic. It would look like the potential of a simple harmonic oscillator. So that's all that means, tachyon. It doesn't actually mean faster than the speed of light. It does mean unstable. Thank you for that question. However, if you look at their calculation, the calculation made some assumptions which would in no way be permitted in today's environment, where the potential of the Higgs field, for example, is calculated with some precision by groups that are doing this kind of calculation, and invariably the potential of the Higgs boson involves interactions with the gauge fields and with the fermion fields with which it couples and to which it gives mass. The electroweak Higgs field, for example, couples to the weak bosons W, Z, and the photon. Or actually, it doesn't couple. That's the one that it doesn't couple to. And it also gives all the fermions masses. It couples to all of the fermions. So the masses of the fermions are extremely important in the calculation of the Higgs potential, for example, especially the mass of the most massive quark, which is the top quark, which is 193 GeV, if I could remember that correctly. It makes a huge difference to the potential. And ignoring those fields, why? The most explicit statement I found was this one from a paper by Sen and Zweiback. Ashoki Sen had proposed that D-branes decayed, but that's not what I'm saying. That's incorrect. It says, since the tachyon is neutral, the gauge field cannot acquire mass by the Higgs mechanism. Now, there's a fundamental misconception going on here. It is true that the Higgs field does not endow the vacuum with a charge. Nevertheless, the Higgs boson carries a charge, and electrons and other fermions and gauge fields that couple to the Higgs boson, its weak charge, even though it's broken, it gives those fermions and those gauge bosons mass. And that is well understood. In particular, the mass that fermions are acquired flips them between their right-handed and left-handed weak components, allowing them to become massive. Okay, so I hope I begin to put a little bit of a suspicion that maybe we shouldn't throw away supersymmetry out of the window right at the very beginning. But I want to talk a little bit now about unification, and I've already talked in this forum about grand unification, because if you're going to talk about string theory and quantum gravity, you're going to have to involve all of the forces. So this was already done. The standard model dates from 1974, 1975. That's when U1 cross SU2 cross SU3, the three forces, became understood as being emerging from these three symmetry groups. And already, right at the very beginning, various people here, Bjorge and Fritz and Minkowski, proposed spin 10. The physicists like to call it SO10, the orthogonal group in 10 dimensions, but spin 10 is the covering group of SO10. They pointed out that it contains the standard model, and not only that, but the charges of the fermions that you see in the standard model mesh with the predictions of spin 10. The other two grand unified groups proposed at that time were SU5 and SU4 cross, spin 4 cross spin 6, which is a Paty-Salam group. And those latter two groups are both subgroups of spin 10. Spin 10 has the property that it contains a whole generation of spinners in one single spinner multiplet. Frank Wilczek pointed out in 1998 that there's a very beautiful way to describe spinners in terms of a bit code. So if you have 10 dimensions, 10 spatial dimensions, actually it doesn't matter whether it's space or time, but suppose they're 10 dimensions, you get 10 over 2 bits or 5 bits, and each bit can be either up or down. Okay, so there's 2 to the 5 things, right, which is 32 fermions of the standard model, including a right-handed neutrino. This is the right-handed neutrino. If I flip its y bit, which the Higgs field does, it flips it to a left-handed neutrino. If I flip what I call the z bit, I've now got a right-handed, these two are aligned, I've got a right-handed electron. If I flip the y bit back up, I've now got a left-handed electron. If I flip 2 of the quarky bits down, I have a red quark with one up red bit. And this one I can see because the z bit is down. This is a down quark. If I change the z bit to up, it's an up quark. And I can see that this is now this is right-handed. I can count the number of up bits. And if it's all up, it's right-handed. And 3 up bits is right-handed. If I flip the y bit again, I get a left-handed red quark. This is not just playing nursery games. This is actually a representation, an accurate mathematical representation of the behavior of spinners. And it's lovely. And this is the way this should be taught in physics courses, not the awful way in which it's currently taught. This can be understood even at the high school level. So it says, this is from a paper with Tyler, which there he is back there, which got published. Thank goodness. It took a while to get this published, didn't it? Yep. And you can see the beautiful arrangement of quarks according to their bits. Now, there's another symmetry on top of this, not just the standard model. There's also relativity, and in particular, the Lorentz group. What do you do with the Lorentz group? Well, actually, it's very straightforward to see what to do with a Lorentz group. The first thing to notice that each of those 32 fermions of the standard model is in fact a Weyl fermion, which means to say it's either a right-handed or a left-handed Dirac fermion, relativistic Dirac fermion. And so it suffices to add one extra bit, and there you have both the standard model and the Lorentz group all in a single group, spin 11.1. So again, the reason this is possible is the well-known fact that the direct chirality, right and left-handed from the point of view of relativity, coincides with standard model chirality, which is actually the same thing as weak chirality, left and right-handed. They're the same thing, aren't they? It's only the left-handed component of a massive electron that interacts with the weak force, and the right-handed component does not. So you add one bit, which I call the T bit, because it's and I painted it gold because it's the most important one. And when it's up, that is a fermion, and I flip it, and look, it's a right-handed fermion. Flip it, it's a left-handed antifermion. It's all very beautiful. Now, I don't want to go through this in detail, but all of this algebra actually works. The game is to express the Dirac four-dimensional algebra that you're all familiar with in terms of this Clifford 11.1 algebra. What is Clifford 11.1? The Brauer-Weyl theorem, proved by them in 1935, states that the algebra of outer products of spinors is isomorphic to the Clifford algebra of multivectors in all possible dimensions. And so if you have spinors in a spin group, as we apparently do, then you have a Clifford algebra by taking tensor products of those spinors. And the tensor products yield, amongst other things, the vectors of the Dirac algebra. And on the right-hand side, these are the 12 vectors of the Clifford 11.1 algebra. And I've labeled them plus or minus because each of them is actually a complex vector. Spinors have an innate complex structure, and that carries over to the Clifford algebra. And so one can express each Dirac vector as a complex thing, and its plus and minus here are the real and imaginary parts of those two things. So the time vector is the same as the time vector in a Clifford 11.1 algebra, but the three spatial vectors are actually 5 vectors. They're grade 5 pentavectors, we will say. And one can confirm that the algebra of the Dirac vectors expressed in terms of Clifford 11.1 agrees with what you would expect for the Dirac algebra. It coincides with it. Secondly, you can check that the Dirac and standard model algebras are mutually commuting subalgebras of the Clifford 11.1 algebra, consistent with the Coleman-Mandula theorem, which has been a big drag because it says that you can only combine, to get analytic amplitudes, you can only combine an internal group and space-time as a direct product. That's only the symmetries that you see, and the symmetries that we see, those are the standard model, do commute. And the Coleman-Mandula theorem is going to be satisfied all the way through. I should have mentioned that the standard model algebra is a subalgebra generated by the bivectors. And there's some tricks that make this happen. I haven't written this down here, but you can see if you take bivector products of these two things, you'll get the Lorentz generators, the 6 Lorentz generators, and each of those Lorentz generators is a rank 6 multivector. So the conclusion is, if you believe that the spinors belong to spin 10, which is the natural gut group to think, and if you believe that it extends to spin 11.1, which makes a huge lot of sense because of the redundancy of the standard model and Dirac chirality, then the smallest group that contains both bivectors, as in the standard model, and Lorentz vectors of grade 6, as in the Lorentz transformations, then the smallest group is the group of multivectors of grade 2 mod 4. So that includes grade 2, 6, and 10 in 12 dimensions. And the 10-dimensional subgroup generated by this is the thing that belongs to the Clifford 10 part. That's if I take away the time part and the longitudinal part and just look at the transverse directions So the transverse group is this 10-dimensional group. It turns out to be U16. You can look that up in Shirokov 2016. And that is a direct product of a U1 and an SU16. And that U1 can be identified, interpreted as generating a U1 spatial rotation of the transverse directions. In other words, here I have, how do I do some Lorentz transformations with this? Well, one way is to do that. And there's another way, which is just to do that. In other words, you can rotate this space-time in 3+1 dimensions and keep the compact group the same. Everything aligned is still a right-handed neutrino. Not obvious, but it works. Now I'll get back to the string theory and ask what does string theory impose? String theory is very restrictive. It's much more restrictive than ordinary quantum field theory. There's not a lot that you can do with string theory. And one of the conditions, which was understood already in 1969 and 1970, was that the gauge group of an open string theory must satisfy the Chan pattern condition that string transform in a tensor representation of the spinor representation. Remember, I showed you that Green, Schwarz, and Witten drawing of a string joining a quark and an antiquark. Well, suppose that quark A belongs to a representation of dimension n, then the string belongs to a quark antiquark dimension group. It belongs to a representation of dimension n squared. And if the string is unordered, yes.
Just what is mathematical difference between the open string and the closed string?
The open string has endpoints, and the closed string closes on itself.
Oh, just that.
Okay. All I've been talking about so far is open strings. I'll get onto closed strings because they're the ones that encode gravitons and therefore general relativity. At least that's the standard picture. Okay, so you can have this tensor product, and it can either be plain like this one, or it can be an anti-symmetric or a symmetric thing, depending on when you flip the indices, whether it goes into minus itself or plus itself. Do it twice and it has to come back. So I just want to remind you a little bit of ancient history. First of all, Cartan was the person. Élie Cartan in 1913 discovered spinors, and he wrote this remarkable book 25 years later describing all that results. It's a beautiful book to read. He discovered that the fundamental representation of any rotation group in any number of space-time dimensions is the spin-half representation, which we will call the spinor representation at the present time. That had not been understood before, that was the fundamental representation. It's the smallest thing that you can have in a spin group. And in even dimensions, there are two spinor representations. One is the conjugate, if you like, the complex conjugate, but I prefer just to say conjugate because it's a generalization of conjugation that's going on. One is the conjugate of the other. And you would hope that antifermions transform in the conjugate. No, it's not quite that way. It's not quite so simple. Never mind. In 1935, Brauer-Weyl proved their theorem, which I already mentioned, hugely important theorem, that the algebra of outer products of spinors is isomorphic to the Clifford algebra in arbitrary dimensions. And Cartan, in his introduction, refers to Brauer's and Weyl's paper as excellent and fundamental. And it is well known to mathematicians who deal with this kind of thing. Yet I was surprised to find that Brauer-Weyl is not mentioned in any of the string theory textbooks, including the three that I've mentioned. And I did a search on NASA ADS, and not a single string theory paper mentions the Brauer-Weyl theorem. I think that's terrible. Weyl in particular, I think, would be spinning in his grave if he knew what was being put in place of the Brauer-Weyl theorem. What I'm telling you today is that the algebra of spinors, fermions, and bosons is related by the Brauer-Weyl algebra and not by the supersymmetric algebra. Why? Because the Brauer-Weyl algebra is the one that we see, and it predates string theory by 50 years or something like that. Okay, so the bottom line of this harangue is the algebra that satisfies the Chan pattern condition is the algebra generated by multivectors of grade 2 mod 4 in any arbitrary number of dimensions. And I can prove that, but I'm not going to do it because I don't have time to do that. And I want to remind you that that was exactly the group that I suggested on the previous slide based on what we see and the requirement that the algebra be large enough to contain the generators of both standard model bivectors and Lorentz generators, which are grade 6. Yikes, it's exact. So in other words, string theory just falls into place. I didn't ask it to do it, it just does. There's some other beautiful things that happen. You know that, the Brauer-Weyl theorem involves not just anti-commutators, but also commutators of spinors. But in the world we live in, apparently fermions satisfy anti-commutation relations. That's familiar in quantum field theory. And so that means not all of the Clifford algebra is realized in an algebra which involves only anti-commutators of fermions. And you ask, what part of the algebra is that? And the answer is the algebra of outer products of like-handed spinors, both right-handed or both left-handed, produces bivectors, that is to say, things of grade 2 mod 4, and those of oppositely handed spinors grade vectors, which are, for example, the vectors of the Dirac algebra. So in other words, this Clifford 11.1 string theory shares with supersymmetry the properties that symmetries are built into anti-commutators of fermions, but the ones that I'm pointed out to you agree with reality, and supersymmetry has utterly failed to make any connection whatsoever with reality. So the model makes very precise predictions. In particular, it predicts that there is a Higgs sector, which is a scalar match, which transforms in the adjoint representation. Tyler and I wrote this paper and showed that that had to be the case. There's a unique Higgs sector, and that Higgs sector is basically the scalar counterpart of the bosonic sector. I'm not talking about string theory now. I'm talking about a grand unified theory in Clifford 11.1. Here, for example, is the electroweak Higgs field, which is part of a 4-component electroweak symmetry. And Clifford 11.1 predicts that if you go to sufficiently high energy, there will be a unification to the Patti-Salam group, spin 4 cross spin 6, when the coupling parameters meet this criterion, and you can read off, this is the running of the coupling parameters, a standard calculation in modern quantum field theory. And so the prediction is at 10 to the 12 GeV. And the color okay, so there's 2 phases. There's first of all a unification to the Patti-Salam group, and that Y disappears, and you're left with weak and color. Those are the spin 4 cross spin 6, wherever it's gone, spin 4 cross spin 6, just 2 coupling parameters. And then this is SU3, then that goes to spin 6, and they meet at 10 to the 15 GeV. However, where the 2 color parameters meet does not necessarily imply grand unification yet. Remember that the grand unified group is actually SU16, and it turns out that the grand Higgs field that breaks the symmetry from spin 10 to spin 4 cross spin 6 is this one right here. It's basically a T bivector modulated by the color pseudoscalar. It breaks SU16 to SU8 right-handed cross SU8 left-handed, and those have the same coupling parameter, so they run at the same rate. So one can basically have grand unification anywhere above 10 to the 15 GeV. And in cosmology, I think I'm going to fast forward over this one. This shows you roughly where those transitions happen, grand symmetry breaking. This is age of the universe in seconds. In cosmology, we have the big astronomical numbers, as you can see. And this is the cosmic scale factor increasing exponentially during the vacuum-dominated phase of inflation, decays into radiation, and then radiation dominated through the three transitions down to recombination, down to the present time, where there's a little bit of dark energy. Right now, the astronomers are trying to measure the equation of state of dark energy by looking at large-scale structure at various redshifts, and a calculation recently published by the observation by the DESI team at that's the dark energy spectrometer instrument spectrometer at KP shows a slight preference for decay, but it's sort of at the 1 sigma level at this point. So you mentioned 26 dimensions, right? So I have a D-brane, which is a fermionic D-brane, and it definitely has 12 dimensions, which is not 26. 26 minus 12 is 14. So you need some extra 14 dimensions, and the bosons can fill out extra dimensions. An example of where this happens was first proposed by the Princeton quartet, Gross et al. In 1984, who came up with heterotic string theory. Heterot comes from the Greek heteros, meaning other, and it means you have bosons in one direction, left-moving bosonic strings in 26 dimensions, combined with right-moving fermionic strings in 10 dimensions. And they did that by compactifying 16 of the 26 dimensions on a rank 16, on the self-dual torus of a rank 16 group, SO32 or E8 cross E8. Those are the only groups that were possible. In the present case, what I have is not that group, but rather SU8 cross SU8, which has rank 7 plus rank 7, which is 14, which is exactly what you want to make up the 26 dimensions. So 12 dimensions on the D-brane plus 14 bosonic dimensions. And it has the properties that one needs. That is to say, one can generate a self-dual torus as string theory requires with the appropriate symmetries. Let me mention a little bit more about the fermionic D-brane. So it's got 10 compact dimensions, and then its longitudinal and time directions. You add those two in with a T-bit, you fill out the 12 dimensions. Now, it's already got to be a complex manifold because spinors have a natural complex structure, and this D-brane must inherit that. Now, a manifold with n complex dimensions, or 2n real dimensions, is called an n-fold, and one with SUN holonomy is called a Calabi-Yau manifold. And Calabi-Yau manifolds have obtained great fame by virtue of the fact that even though they're highly curved, nevertheless, they carry zero energy momentum, which is a highly desirable thing in the vacuum that we see today, because it looks as though, apart from this tiny dark energy that we see, it looks as though the vacuum is practically empty of energy momentum. Now, in the theory that I'm putting forward to you, the symmetry breaking is just Higgs symmetry breaking. And what does Higgs symmetry breaking do? It breaks down the gauge group. Now, the holonomy group must be a subgroup of the gauge group. Why? Because the gauge group describes the symmetries on the D-brane, and the holonomy group is the group of when you rotate an object around a closed loop on that geometry, by what group have you rotated that thing? So it must be a subgroup of the holonomy group. Now, the Durand theorem says that if your holonomy group is a product, then the underlying manifold is a product. However, that only applies to the simply connected components, and a U1 component is not simply connected, so it doesn't contribute. The conclusion is that the spin 10 holonomy, remember that's the maximum holonomy of a 10-dimensional manifold, it's a subgroup of the total gauge group. So it breaks to the Patti-Salam group, and this is a complex manifold it's a twofold, it's 4 dimensions. This one is 6 dimensions, it's a 3-fold. And then when it goes down to the standard model, the spin 4 goes to U1 cross SU2. This one doesn't contribute. This contributes a Calabi-Yau twofold, this one a color Calabi-Yau threefold, and then electroweak symmetry breaking to the present time gives you the U1 electromagnetic group multiplied by the color group. Then we have a flat twofold multiplied by a Calabi-Yau threefold. So what I'm saying is, this predicts that the compact geometry that we don't see in the higher dimensions in the fermionic part has the structure of a Calabi-Yau manifold, not because a posteriori I needed it to make the vacuum, but rather because that's a property of the gauge group that we see. There's a few beautiful things that happen on here. I'm not really going to go through this whole slide, but it is usual in the string theory textbooks and on the reviews to assume from the outset that space-time is Minkowski so that you can quantize it. Quantizing on a Calabi-Yau manifold, you'd think would be, well, that's a much more difficult thing because it's highly curved. However, it's actually, if you have open strings only, it's really quite straightforward. What you do is you take your two string coordinates, you do a Wick rotation, and you then transform them into the Z and Z bar, a complex coordinate and its complex conjugate, and then the string wave equation looks like this. And normally these coordinate connections, also known as Christoffel symbols, those vanish in flat space, and you can say the solution of the wave equation is the sum of Z and Z bar left moving and right moving modes. Well, there's another way to solve this equation, which is to say you've only got holomorphic modes, holomorphic modes, and only this one, this goes away, this goes to 0. So again, this whole term vanishes, but that only works for open strings. The answer is that if you have open strings, you can have propagation, you can quantize this thing on a curved manifold. Gravitons. Gravitons emerge in the usual way as massless eigenstates of closed strings, and they are obtained as direct products of open strings. Okay, a spin 2 thing gets to be a direct product of two spin 1 things. That's another mathematical statement here. Now, the closed string in an open string theory with fermionic endpoints, the closed string has no endpoints that terminate on the boundary. So it cannot carry charge because that's where the charges are. The charges lie with the fermions on the endpoint. So a closed string carries no charge. But not only is it chargeless, it must be a gauge scalar. By contrast, for example, the photon has no charge, but the photon is the carrier of the electromagnetic field, and it transforms under the non-trivially and the electromagnetic transformation. Now, what I'm saying here is a closed string in an open string theory like this, closed strings are fine, but they have to be a gauge scalar. And that means that you have to take a trace over the sum of, take a trace sum over the possible open string products that you have. And the result is just two sets of particles. One is spin 2 gravitons, which can be this way or this way, they're their own particle. And the other way of combining spin 1 things as a trace is to give spin 0, and those are well known to string theorists. They're called the dilaton. And again, there are two of those, and one is it is its own antiparticle. There's no sign of a dilaton, but on the other hand, any particle which has 0 spin can have a potential associated with that. That is a standard feature of particle physics, including string theory. And it must be, since we do not see a long-range force associated with spin 0, this is something that is speculated for decades in the general relativity. There's no evidence for it, so it must be massive. And because it interacts only with gravitational strength, it interacts extremely weakly, which means effectively its decay time is very, very long, and that means it's a stable particle. So a stable massive particle could potentially be the cosmological cold dark matter.
Excuse me.
Yes.
How would one go about computing the dilaton potential in your framework?
I don't want to calculate the dilaton potential yet. I think the first thing to do is to calculate the tachyon, open string tachyon. potential. And then we can worry about things that we can't see. If the tachyon, okay, I'm hoping that Deviani, who's going to Berkeley in the fall as a graduate student, might take this on as her PhD thesis, because it's relatively straightforward to do the calculation correctly for the first time, including the interactions of the potential with fermions and gauge bosons to which it couples. The tachyon definitely couples to all of those things. And that is a straightforward calculation. If you can find that there's a stable quartic term, then open string theory is back in business. If it's not, the string theorists will be very happy because it confirms their prejudices. So another magic thing happens. The vanishing of gauge and gravitational anomalies in superstring theory was a mathematical miracle, which ushered in the first superstring revolution by Green and Schwartz in 1984. By contrast, gravitational and gauge anomalies vanish almost trivially in this particular theory, because a sufficient condition for these anomalies to vanish is that you have right and left-handed things in the same representation, fermions in the same representation. And right, we have exactly that. We have right and left-handed fermions in two matching representations. So anomalies vanish trivially. Isn't that nice? Not much work necessary. And then just to comment, there's three generations that we see: electrons, muons, and tauns. And already early it was understood in 1985, the work of, again, Witten's name is on this, but Phil Candelas pointed out that there's a topological relationship between the number of generations and the Euler characteristic. In particular, the number of fermions is half the absolute value of the Euler characteristic. And that corresponds to 3 along this axis, six in either this direction or that. This is taken from a review paper by Heyerdahl, labeling all the Calabi-Yau manifolds that are known. And red means there's a lot of them. That means the logarithm of multiplicity, and you can see it goes up to e to the 12, so it's about 1 million. Okay, so there's a lot of these things. And there, as it says here, there are numerous of them known. And if this is the theory, then we might be able to figure out which Calabi-Yau manifold describes our universe. That would be really nice. So I'm going to leave up my summary, and we've got 10 minutes for questions.
So, thank you very much.
Other questions? Yeah, Robert.
Well, I'll give you one minor question. Clifford 11.1 is, from your point of view, nice because it's the smallest Clifford algebra. What can one say about larger Clifford algebras?
Well, you're very welcome. I come from the philosophy of an astrophysicist, which is we don't try and invent things. We take what we see and we try and figure out what we see. But I do have an argument that it may not be larger than that, which is to say that the gauge bosons that we see are not all that there used to be because of symmetry breaking, right? The W bosons and the Z bosons are massive, and there's presumably some other bosons sitting up at grand unification. They disappear rather easily. It's difficult to get rid of spinors because in all dimensions, they stick either up or down. You can't make a zero out of them. By contrast with the boson, it can be +1, 0, or -1. And the 0 means you can go away. So if that interpretation, which is only, again, this is me trying to look at nature and saying, what are you doing here? It seems to me there's an argument that can be made that the fermions that we see are perhaps all that there are. And that is the most logical thing to follow up at the present time. I can make a more complicated argument than that, because it turns out that 4 mod 8 dimensions has all the nice properties that I've mentioned. So if you wanted to go to higher dimensions, you probably need to go to a 20-dimensional D-brane. And then that probably wouldn't work with the Chan pattern argument. This one just works.
Right. That second argument is perhaps a bit more convincing than the first. The
Okay.
first argument seemed to have about it something of the flavor of the anthropic cosmological principle. Something about the only fermions we see and all that having something to do with the fact that they are the only ones that could be there. You take my point out.
Oh, I do. But you're welcome to explore. What I do think is important is that string theory move on from where it is at the moment. It seems to be stuck with supersymmetry, and that is just not necessary. There needs to be work done. There's a lot of work that can potentially be done. And the good thing about this is this actually brings string theory, if it's correct, back into the realm of testable physics. It's not sitting up in the stratosphere where we can't access it. We can access it potentially right now by comparing the predictions to what we see at the Large Hadron Collider and whatever other instrument we build of higher energy in the future. Tyler.
Yes, I just want to say it's not quite an anthropic sort of reasoning.
It has that flavor.
It's more
in my
so-
way of thinking anyway.
Yeah, I guess I get what you mean. It's more so just an aesthetic argument. But
Yeah,
if it were purely this statement of, oh, we see, we only model the things that we see, then we would have to be forced to choose an even smaller group, I think. So like the arrangement you have right here is a right-hand neutrino. So my question is, why don't we see any right-hand neutrinos? And how does that, and maybe this is something that this predicts that we can observe in the future.
Back in the old days, when we thought that neutrinos were massless, that meant they had to be purely left-handed. But then we discovered, when I say we, I didn't do it, physicists discovered that from the oscillations of neutrinos, first of the solar neutrinos and then atmospheric oscillations, that at least 2 of the 3 generations of neutrino have some mass. And if they have mass, that means they cannot be purely chiral. They cannot be purely right-handed and purely left-handed. And what that means is there has to be a right-handed neutrino, and the left-handed neutrino that we see must be a linear combination of mostly left-handed with a little bit of a right-handed mixture. That is to say, the mass eigenstate is not quite the same thing as the weak eigenstate. And likewise, the right-handed neutrino has to be a mixture of the two, the mass eigenstate. The right-handed neutrino, there's something called the seesaw model, which relates the small mass of the left-handed neutrino to the large mass of the right-handed neutrino, saying the product of those two is essentially of the order of the Dirac mass. And if that's correct, that would put the right-handed neutrino mass up at 10 to the 12 GeV. So it works. It's the quotes belief in standard particle physics theory today is it's more likely that the right-handed neutrino exists, because if it didn't, the left-handed neutrino would be massless, and it isn't.
What happened with this notion of supersymmetry breaking supersymmetry?
What happens to supersymmetry breaking? We don't have any supersymmetry here. So if you have supersymmetry, then you need to break supersymmetry. And there was an argument it had to be not far above the electroweak scale, but since everything up to 1 TeV had been ruled out, they say, oh, you're going to see it just above a TeV, and we've been running at 13 TeV since 2015, and no sign of any supersymmetry. The problem with supersymmetry is not only does it predict superpartners that you don't see, but it also predicts other fields which break those symmetries, which we also don't see any sign of. And it's possible that some of those symmetry breaking fields are the same as the fields that we don't see, and that's called the minimal supersymmetric standard model. And all that the Large Hadron Collider has done is ruling out swathes of the most obvious place where that might exist. What I'm saying is there is no supersymmetry at all, and therefore no problems. Supersymmetry predicts so many predictions, at least one particle for each particle that we see, and none of those superpartners are observed. And the graviton, for example, comes in a multiplet, which includes, for example, the spin 3/2 gravitino and possibly more gravitinos, so it could be up as many as 8. The graviton could be part of a multiplet of a dimension 256, for goodness sakes. And we only see the graviton. What's wrong with that? What I'm saying is the number of predictions is astronomically huge and none of them work.
You mentioned ADS about 10 slides ago. Is that anti-disturbance?
ADS, did I mention ADS?
Yes, you did. Yeah.
No, it's the NASA ADS.
Oh, the ADS, that's the NASA ADS database
Right.
where you can look up stuff.
Do you have anything to say about ADS?
Well, ADS
That's down here.
ADS CFT is premised, or at least the version that I know of is premised on supersymmetry. And I'm afraid I just throw that out of the window. I work on black holes. That's what got me interested in this high energy stuff. And I have to say I got extremely frustrated with the high energy physics literature because it doesn't provide anybody who wants to use high energy physics anything of any use whatsoever. So I felt like now I'm forced to go and figure out a theory that actually works. I see you looking at your watch. It's probably time to stop, isn't it?
I think that was Shigen, you had a question?
I can ask it afterwards.
Okay. So any more questions? Then thank you. Let's thank the speaker again.
Thank you, Marcus. Thank you, everybody, for coming.
Yeah, and actually we have one more talk this semester next week. Okay, thank you.
Thank you, Marcus.